What we're going to be covering this week is the very last information and chapter or section on geology. So next week, obviously, we're going to be getting into a brand new unit. So if you're kind of sick of geology topics, then that should get you kind of excited that we're moving on to something brand new. So I'll kind of save that for next week. So obviously this week's section, because we are finishing up some information, will include a little test or quiz along with the assignments as well. So it's a little bit of review of some information from last week with some new stuff towards the bottom here. So you can see this is titled Earth's Interior. So more specifically, we're going to get into some things that happen then in Earth's interior. So again, if you really like this topic, if you're thinking, wow, I really enjoy this, maybe this is something I might pursue later in life, then the study of this is more than just being a geologist. That's what number one is. A specific geologist that uses seismic information to interpret the characteristics of the Earth. That particular career path would be called a seismologist, S-E-I-S-M-O-L-O-G-I-S-T. So really, most Pennsylvania schools don't have this career as an option because, again, we're not tectonically active around here. So you might have to go out to California, UCLA, places like that. And they have smaller colleges as well that have that degree program. All right, so number two, as energy or seismic waves pass through material, it could be bent, so it changes direction, bent in different direction. It could be absorbed, altogether, and we saw that the outer core kind of absorbs the S waves, and it can speed up. It can definitely make waves speed up. So number three, if the Earth were uniform meaning U-N-I-F-O-R-M, uniform or the same throughout in structure and composition, then it would be very easy to predict where earthquakes were because we would know exactly how they were going to travel, where they were going to travel, how fast they were going to travel. But we're not like that. Our interior is made of the crust, mantle, inner and outer core, and there are different thicknesses and different materials that make that up. So that makes studying and learning about earthquakes quite challenging. All right, some of this Part B information was part of the last section as well, but what do we call the boundary that marks a density change between layers? That's called the MOHO discontinuity, which you can also see as part of number 2. So you can just write MOHO for short if you want to. Remember, the MOHO is the boundary between the crust from the mantle, or the upper mantle in this case. Again, that's where seismic waves tend to speed up. Number 3 is also from the last section then. Shadow zone, remember the shadow zone is the area that's always, again, think of the Earth as being completely round, 360 degrees. So shadow zones are the areas that are always 105 to 140 degrees, again, where no seismic waves are detected. Again, the shadow zones, really number 4 then, is proof that the outer core must be in a liquid state. Because again, the S waves cannot travel through the liquid outer core. That side-to-side motion that S waves have, they can't go through the liquid outer core. All right, number 5 then, the inner core is denser. It does allow P waves to pass through, but they're bent and definitely redirected along in different directions. So the inner core is the answer number 5. Now, number 6 and 7 then are special names that we give to different parts of Earth's interior. These aren't part of the official 4 layers, but they're definitely layers that scientists have learned to identify the interior of the Earth. So number 6, the crust and upper mantle together make up what's called the lithosphere, L-I-T-H-O-S-P-H-E-R-E. The lithosphere is really just the tectonic plates. So like when you hear the word tectonic plate, think lithosphere. They mean the exact same thing. Below the lithosphere, then, is the driving mechanism, the thing that makes the tectonic plates move around. It's where the convection cells are, convection currents that spin and cause the tectonic plates to either move apart or come together. But anyways, that layer, then, that exists within the mantle where the convection currents are has a very special name. It's called the asthenosphere, A-S-T-H-E-N-O-S-P-H-E-R-E, asthenosphere. All right, the last section then that's part of this last topic then is volcanoes. Volcanoes obviously are a pretty cool topic, and I've got some pictures on the next page of the different types that we can examine in a little more detail. But number 1, magma rises to the Earth's surface because it's less dense than the surrounding rock. Think about it. It's one of the few things on Earth that actually goes against gravity. Magma is always rising up through cracks in the Earth's crust. You think, well, it's pressure, it's heat and pressure, like heat rises. Well, that's not true for magma. It's the fact that it's less dense, that magma material is less dense is why it rises up. So magma reaches the Earth's surface at two general places, plate boundaries and, letter B, something called a hotspot. Hawaii is a great example of a hotspot. The Hawaiian Islands are smack dab in the middle of the Pacific plate. They're nowhere near tectonic plate boundary, but yet, obviously the volcanoes or the Hawaiian Islands are volcanically active, and that's because they exist at a hotspot. Hotspots are just areas of the mantle that material rises up through them. Yellowstone National Park in our own United States here, we have a magma pocket that sits kind of close to the surface, and that's what creates the geysers that exist at Yellowstone. All right, number 3. All solid material that's ejected from volcanoes, whether it's the ash, the soot, the rock materials, those are called pyroclasts. Pyroclasts, pyroclasts. So like when a volcano erupts explosively, sometimes you'll hear it referred to as a pyroclastic explosion. All right, number 4, measure of the resistance of fluid flow. That's called viscosity, viscosity. So one thing that scientists are always looking at with volcanoes is the viscosity of the magma. Very viscous, things that are flow freely and they're not that thick, tends to produce quieter eruptions, whereas thicker magma can cause quite explosive eruptions. So volcanic eruptions vary in different ways depending upon the magma's viscosity or composition, same thing. All right, so getting this last part then, there are 3 general types of volcanoes here, and you can kind of look at these 3 types. There's some basic drawings. Since I already mentioned the Hawaiian Islands are a type of volcano called a shield volcano. These are the ones that are huge. They're very long, broad, sloping sides. They generally do not erupt violently. Usually they have just magma that kind of oozes out. Maybe volcano jumps up into the air. Not jumps up, but erupts maybe in the air 50 feet, 100 feet. That's considered awfully a quiet eruption. They tend to occur over hotspots, and they are the largest volcanoes by and far. That's shield volcanoes. Composite volcanoes, if I asked you to draw a volcano before I share this information with you, chances are this is the one you would have drawn. These are the ones that look like mountains, basically. They have violent and explosive eruptions, ash, steam, gases, pyroclastic flow that comes from them. Mount Rainier, Mount Fuji, Mount St. Helens is a very famous eruption here in the United States from the 1980s. Basically, they have alternating layers, and that's why you kind of see these stripes throughout this picture up here. But yeah, they're really big mountain-sized volcanoes. The ones that we don't really have in the United States, they're more common in other places in the world, called cinder cones. These are the ones that are smaller in size, but they're really steep. They have like steep sides here. These could be a few hundred feet high. They're definitely not mountain size like the composites. They're usually found near larger volcanoes there. They're kind of like the subsidiary ones that kind of sit off the side. So they're smaller, steep volcanoes. Again, they're the smallest. They are the most common type because they, again, aren't very big. And they mostly come from violent eruptions. But again, they're not big and explosive like the composite volcanoes that can cause widespread damage over hundreds of miles, basically. They can actually affect global weather conditions if the eruption's bad enough for composite volcanoes. So as you look back at here, first one then, smaller, a few millimeters high. So it's a cinder cone, obviously. Number 2, broad flats, layer upon layer of lava, Hawaiian Islands, that's shield volcanoes. And again, the third one, the ones that you think of that are big and explosive, these are the composite volcanoes then for number 3. All right, so there are some assignments with this section. Like I said, there's also a quiz or a test with this section as well. So use your information to help you out with that.